Hello everyone at CVMP. I hope you and your loved ones are well in these times. It is my absolute pleasure to welcome you to this talk about Intel Studios. My name is Krejov, former software architect at the studios. We have a lot to cover, so let's get started. First, for the benefit of those not familiar, let me begin by introducing what was the world's largest volumetric capture stage until its closure as of late this year. Capable of capturing and reconstructing 30 people simultaneously, it enabled never-before-seen digital recreations of performances that could be enjoyed from any angle, with devices such as your phone, your tablet, or virtual reality headset. With a capture area of 10,000 square feet, it was capable of reconstructing an entire theatre production or musical with room to spare. This unprecedented scale first and foremost enabled real performances to be captured, but also brought a unique set of challenges. Now, just in case you hadn't seen it before, here is our show reel released earlier this year at SIGGRAPH.
This is Intel Studios. This one-of-a-kind studio means you can experience a look at human performance that you won't see anywhere else in the world.
Now let's take a look at what it took to create these unique productions. Let's start with the stage itself. Quite simply, a big green dome. Job done, the end. I'm of course joking. Looking in from this metallic and cloth structure were 100 8K cameras, each with high quality configurable optics, all connected through fiber optic cables to a dedicated server farm within the same building. Yet there was so much fiber cable that it in fact spanned further than 5 miles in length. With these 100 unique views, we could perform volumetric reconstruction and free viewpoint rendering from almost any conceivable viewing angle. But as I mentioned before, this is challenging for a number of reasons, including synchronization, recording, and processing such large amounts of data. Along the way to solving these problems, we also found opportunities to develop computer vision and machine learning algorithms that made our productions possible. Our on-site render farm consisted of over 90 Intel-powered servers with more than 10 petabytes of storage. This farm was designed to manage both our recording from all of our cameras and the post-production of our content. Recording from our 100 cameras peaked at an insane rate of 1 terabyte every 10 seconds, making storage and archival costly, and it required the development of a volumetric-based compression algorithm for dealing with the raw data, and preserved using a lossless shrinking that managed to reduce it to 1/10 of its original size. The studio did not always have 100 8K cameras, and in fact, the first production, which was shown at CES 2018, shown here, utilized 36 5K cameras. We also had a constraint on how much data we could record, with the limit being 30 seconds of continuous capture. This was while we were waiting for buffers to clear, and driven by director's feedback and some challenging workarounds that we did, we upgraded the system such that we could record for a continuous 2-hour period, and in theory produce a one-shot volumetric feature film. Besides viewing angles, there are also a number of benefits that come from capturing action as a volumetric scene. First and foremost, many of the processes of traditional filmmaking can be moved to the post-production stage. For example, set design, lens selection, lighting configuration, and even the action itself can be changed in post, allowing the director more flexibility to adapt to the content in editorial. Secondly, the hardware configuration between projects is largely unchanged, allowing a range of production types to be captured and produced back to back, a real advantage for today's fast-moving and varying content platforms. Producing our volumetric content was a multi-stage process, beginning with pre-production decisions regarding the particular project, often regarding the color green, but also the design and alteration of props such that they'd meet the algorithmic requirements. Production days then consisted of performance capture and the collection of our required lens, color, and lighting calibrations. The content had image processing applied to remove lenses and sensor artifacts before reconstruction. The sequence would then be reconstructed with additional point cloud processing being applied, such as face tracking or frame interpolation, examples of which I'll show shortly. It's at this stage where we'd apply post-processing effects before distributing either through 2D edits or as a 3D game engine asset. As I mentioned during production days, we would capture calibration shots that enabled the localization and characterization of the cameras and lenses. We sought after high-quality calibration performance while also reducing the process overhead so that we could move quickly into filming the actual content, as production time at this scale is very costly. From having worked on the refactoring of our calibration, it quickly became clear that achieving the minimal reprojection error was a crucial step to providing the quality of reconstruction needed. It cannot be understated how important it was to solve when you consider that we had to recover the detail, such as this chap's tattoos, from as much as 50 feet away. Once the differences between the cameras were normalized, image processing looked to retain as much detail as possible. As it is at this scale, every pixel matters. The image pipeline was responsible for dealing with trade-offs in optics, such as vignette and chromatic aberration, while unavoidable camera noise was addressed prior to edge-preserving debayering. Now that the images were corrected, we could reconstruct the scene using spatial carving, which was accelerated using a hierarchical subdivision for each of the characters, props, and environment. This carve was combined with N-view stereo to add the additional capability of managing concavities. As with many carving approaches, the greatest challenge was to generate a segmentation mask against the background, and given complex scenes, we would most often use chroma key and luma-based rotoscoping. Certain conditions would cause errors in masking, needing additional work using our in-house developed tools. These were capable of eliminating cameras that suffered from specular glint, for example. It is at this point that we also looked at several methods for automatic segmentation, including the world is your green screen, but found that it did not generalize well given the scale of our images and the focal length we were using. But we did start to see some promising results with specifically trained models. Using a combination of geometry and artificial intelligence, we then estimate surface normals, which were required for relighting and texture spattering. We also found some of the process of cleaning our reconstructions could be done as a post-processing step, as we could compare the result of our reconstruction to the underlying images through back projection, identifying mistakes in geometry or texturing. The following shows an example of some of the sort of improvements we would find through adjusting our calibration and reconstruction methods, and found that we were starting to near photorealistic reconstruction that would meet the demanding expectations of the film industry. As a side note, part of our calibration process would involve the collection of images of our set without cast being present, as to enable the recreation of our set design using photogrammetry, as a digital backdrop for two main reasons. The first being the obvious use in our scene, but secondly, providing a cue for segmentation as synthetic backdrops for training of machine learning methods. An example of its use is in our CES demo, which shows we could in fact render the cast and set from impossible perspectives of, for example, the horse riding to the rescue. Like I mentioned before, we'd also develop a number of post-processing tools for creating cool visual effects that could be used for driving the narrative, such as character tracking, shown lower middle, stylized shaders in the lower left, and my personal favorite, better than native slow motion. The lower right corner shows this in action, where we could create a shot with super slow motion running at 120 frames per second, despite our native frame rate being a mere 30. This sort of post-capture enhancement was really just the tip of the iceberg, with us having the ability to track every single point in our scene. So now the scene has been reconstructed and had effects applied, let's look at just 3 examples in which we deliver our finished articles. At this moment, we see our view-dependent rendering being used to put 2 characters captured on our stage within a real office space. The position of our virtual camera used for rendering the characters was placed to reflect the real position of the handheld camera used to record the office setting. And so while this is not the most exhilarating example of motion picture history, it does show the visual quality that could be achieved in a well-lit and relatively static scene. It is really just a short hop of the imagination to see this being used in a more complex and visceral action sequence, or as part of a digital workflow for your favorite TV show. Now, let's pick up the pace and take a look at a behind the scenes of our emotional VR story, Queer Skin's Arc, released earlier this year.
This is a story of a young gay physician who's estranged from his rural Catholic Missouri family who dies of AIDS in 1990. I'm Ilya Silak, writer and director. We're here today at Intel's volumetric capture studio shooting Queer Skin's Arc. It was really important that we didn't try to make an experience that made you pretend to be someone that you weren't. So we really wanted not to dictate how people should feel about this story, in which the man who's died, Sebastian's mother, reads his diary and allows herself to imagine him alive and in love, and this dance is part of her imagination.
I'm Brandon Powers, the choreographer for Queer Skin's Arc. The choreography is integral to this story because it allows us to tell the story of Sebastian and Alex throughout their relationship by kind of jumping through the journal pages. And we use different segments choreographed with different nuanced movement styles to capture the aggressive and powerful moments in their life, and then the softer, more intimate moments. The visitor is able to witness that and actually sense what that feeling was like in their life, as opposed to just hearing words or reading that diary for themselves.
Part of the story uses interactive dance to bring the visitor in close connection with the main characters. First of all, we don't ask you to dance, but however you move in the space, your body and hands will leave a trace of light, and how you decide to use that space will actually influence how the dance transpires. So it makes you and your movements an integral part of the storytelling.
I'm Cyril Cebulski, creative and technical director. We chose this medium because it's a spatial medium, and we really wanted to use the affordances of VR to tell the story. We're really interested in creating new forms of intimacy, and I think this medium lends itself to that particular goal.
Volumetric is absolutely critical to this experience. And the reason is this is such an intimate story. We wanted to make the visitor feel that these people were really there, really alive with them, and only volumetric does that.
And to wrap things up on an upbeat, here is our showcase of our superhuman AR experience created in collaboration with SM Entertainment. Thank you everyone for taking the time to listen to my talk, which I hope you enjoyed. I would love to be able to take this opportunity to tell you about what I'm working on next, as it's very exciting, but it is still very much early days. So with that, I'll point you to my personal pages, and until next time, thanks again.